The section 1.7 summary of inverse functions from the OpenStax PreCalculus book. This will be the full summary, so I'll go through and try to explain everything to somebody who I'll assume has never seen this stuff before. A couple things I want to remind you of before I get into the main topic of this section, which is inverse function. A couple of things that came from section 1.1 actually. Our definition of what a function is and our definition of what a one-to-one function is. So really, I think it's easier to remember what's not a function, and basically this picture is not a function. And what's not one-to-one, this picture is not one-to-one. A perfectly good function, not one-to-one. Hopefully you remember these two things. It's really important. In order to be a function, every single element in the domain must be mapped to exactly one element in the range. So what I'm saying is it could not possibly be the case that you have one element in the domain that goes to two different elements in the range. If that happens, it's not a function. That's important, and I'm not just refreshing your memory. This will be relevant to this section. Furthermore, it's perfectly fine to have two elements in the domain mapped to the same element in the range. But when that happens, we have a name for it. We say the function is not one-to-one. So anytime something like this happens, our function is not one-to-one. If this never happens, our function is one-to-one. Here's a little bit more of a definition. Why do I bring that all up now? Well, it turns out it's very relevant when we talk about inverse functions, which is the topic from section 1.7. So here's the idea with inverse functions. We understand what a function is. It's this mathematical machine that we're putting things into. Usually we use the letter x to denote a generic input, and something else comes out of. If our function's name is f, then f of x is what would come out of it. This is a function. So you could have the doubling machine, for example, and you put a number into it and double that number comes out. You put 5 in, 10 comes out, etc. If we have a function, turns out not all functions, but for some very special functions, and I'll hit on the criteria later, we can define this thing called an inverse function. And the inverse function is what section 1.7 is devoted to. And the idea with an inverse function is you can kind of think about it as undoing your original function. It's your original function being ran in reverse. So what it does is it takes in the outputs from your function and it gives back the inputs to your function. Okay, that's pretty broad and maybe a little bit confusing. Let me start you off with an example. Maybe I have a function f of x equals 3x. Right, that's my function, and I can even write it in function notation if that'll make you happy with my little flow chart going on here. F of x equals 3x. If I put the number 6 into this function, I don't know where 6 came from, 18 would come out. Perfectly fine. For this function, I can define this thing called an inverse function, and the notation I'm going to use will be an f with a little -1 up in the superscript here. This does not mean f raised up to the -1 power. This is just a symbol that we use to denote the inverse function. And what the inverse function does is it takes as its inputs a number like 18, and when 18 goes in, 6 has to come out. So it runs this function in reverse. Instead of the 6 being the input and the 18 the output, the 18 is the input and the 6 is the output. You might, if you're clever, be able to come up with the rule of this inverse function. Especially if you listened to me when I was saying how what the inverse function is undoes this thing. So how do you undo tripling something? Well, you cut it into a third. You divide by 3. For the function f of x equals 3 times x, the inverse function is f of x equals 1 over 3x. And that makes sense, right? To undo tripling something, you divide by 3. For the function that adds 4 to an input, I would subtract 4 as the inverse function. When functions get too much more complicated, we won't be able to just intuitively figure out what their inverse function is, but we'll learn how to deal with it. Inverse function, definition of an inverse function, the way I think about it is it's just another function that undoes what your original function did. And I know that's not the most concrete definition, and perhaps you want to see something with more vocabulary words. Feel free to reference your book. I think having an intuitive understanding is more important, and the intuitive understanding of an inverse function is that an inverse function undoes what your original function does. That's your definition. 4 implications of this definition. It turns out that there's a lot to inverse functions, that defining a function in this way raises a lot of different questions and makes a lot of different points. 4 points that I really want to hit on. The first one is that if I have a function that's not one-to-one, I will not be able to define the inverse of that function. Wait, wrap my head around that for a minute. If I have a function that's not one-to-one, okay, here's a very generic picture of a function that's not one-to-one. Maybe I can come up with something a little bit more concrete. What if I had what's the not one-to-one function that comes to mind first for me is x squared. And this function is not one-to-one because if I put the number, I don't know, 2 into this function, 4 comes out. But if I put the number -2 into this function, 4 also comes out. And that's fine. That doesn't mean it's not a function. That's a perfectly good function that can happen. It just means it's not a one-to-one function. However, if I tried to define the inverse of this function, I would have a big problem. Because when I put the number 4 into this inverse function, the machine would get all confused. It wouldn't know what to kick back. It would want to give me back a 2 and a -2. So what? So have it give you back a 2 and a -2? It can't. Why not? Because of this. Because of this right here. To be a function, we cannot have one input have 2 different outputs associated with it. It's perfectly fine to have 2 different inputs associated with the same output, but if you're in that case, you can't switch the direction of the arrows, because if you did, you'd end up with something that's not a function. What I'm saying is that for this specific function, I cannot define an inverse function. You might have thought that the inverse function would be the square root of x, and you'd be damn close, but it's not quite right. We'll figure out something we can do to kind of get around this issue later on, but the first of the 4 implications that I really want to hit on is that if I ask you to find the inverse, anybody, any teacher asks you to find the inverse of a function, and that function is not one-to-one, they're asking you an unfair question. You cannot find the inverse of a function that's not one-to-one. So what do you do in that case? Well, we're going to learn something later on. We're going to learn a way to change our function to make it one-to-one so that we'll be able to define its inverse. But right now, when we're just getting comfortable with these things, an important criteria that has to be there anytime you're asked to find the inverse of a function is that function must be one-to-one. Note that the tripling function is one-to-one. If you graph this thing, it would pass the horizontal line test. But this function is not one-to-one, so I cannot right now ask to find the inverse of it. That's the first of my 4 implications. To find the inverse of a function, that function must be one-to-one. Note that my next learning objective here will be finding the inverse of a one-to-one function. That's because I can't just say finding the inverse of a function, because if it's not one-to-one, I can't do it. That's the first implication. The second implication that I want to get at really comes from this picture right here. What an inverse function does, you can think about it as undoing this machine. You can also think about it as switching the inputs and the outputs. The point that I'm making here is that if 618 is on the graph of f, meaning when you, in other words, f of 6 equals 18. If I have some function, and when I put 6 into it, 18 comes out, that means the point 6, 18 must be on the graph of this function f. That tells me a lot of stuff about the inverse. I immediately know that f inverse of 18 must be equal to 6. I immediately know that the point 18, 6 is on the graph of f inverse. Because f inverse, the inverse function, is a function in its own right. So everything that we asked before about functions, I will later be able to ask you about inverse functions. And it turns out we can answer a lot of those questions just based on what we already know about functions and the fact that an inverse function switches the inputs and the outputs of the function. That's so important that I consider it the second major implication of this definition. The second one being that an inverse function switches the inputs and the outputs of your function. So if this point is on the graph of your function, this point is on the graph of your inverse function. If this input leads to this output in your function, this input leads to this output in your inverse function. That's the second implication. The third one, really I could call it 2b. It's really related to the thing that I just said. Recall that the set of numbers you're allowed to put into your function is called the domain of the function. And the numbers that can come out of your function is the range of the function. But the numbers that come out of the function are exactly the numbers that go into the inverse function. And the numbers that come out of the inverse function are exactly the numbers that come out of the function. So the third implication of this definition, and it's really another way of stating that we switch the inputs and the outputs, is saying that the domain of the function is the same as the range of the inverse function. And the range of the function is the same as the domain of the inverse function. Because all the inverse function does is switches the inputs and the outputs. And the possible inputs are the domain, the possible outputs are the range. The fourth and final implication of this definition goes back to function composition. Imagine if I compose together these two functions. And so function composition, that's something we learned a couple sections ago, where essentially you run one of the machines and then you run the next machine sort of in parallel. So I take some input and I put it into the function does its thing, and then I let the inverse function do its thing. The input here will be the output from here. Well, essentially I'll just be recycling, right? I'll put some number in here and the function will mess it all up and give me some other number, but the inverse function is defined in a way that it'll take that messed up number and undo everything to take me exactly back to where I started. So what I'm saying is if I compose together a function and its inverse function, whatever I put into that composition will be exactly what comes out of the composition. If you put 6 in to f inverse of f of x, f inverse of f of 6 will be equal to 6. Because if I put 6 into my function, 6 in right here, 18 comes out, but then 18 would be what would be going into my inverse function, and when 18 goes into my inverse function, 6 comes out. Similarly, f of f inverse of 18 would be equal to 18. If I take 18 and put it into my inverse function, it takes me to 6, but I know that if 6 goes into my function, 18 comes back. And there's nothing special about 6's and 18's. I use those just to illustrate it with this example. It's true for any value of x. F inverse of f of x equals x. F of f inverse of x equals x. Composing a function with its inverse function in any order gets you x. F inverse of f of x is the exact same as f of f inverse of x, which is equal to x. Doesn't matter what you put in, if you do a function and its inverse function in any order, what comes out will be exactly what had gone in. That's all that I'm saying. That's the fourth implication of this definition. That's a whole lot of theory. I didn't do a whole lot of examples there. I just really wanted you to understand all the important things about inverse functions, and really there's a lot of important things about inverse functions. But once you wrap your head around that, I can move on to actually doing some examples, which you're probably pretty eager for me to get to. And really there's two different types of examples that I want to do. I want to be able to find the inverse of a function. So give me some one-to-one function. We could have done it with 3x, but let me choose something a little bit more complicated. G of x equals, I don't know, 2x plus 1. It's a function. Not only is it a function, it's a one-to-one function. I can put numbers into this function, other numbers come out, and I can't find two different inputs that would yield the exact same output. This is a one-to-one function. Because it's a one-to-one function, I could ask you to find g inverse of x. I can ask you to do that. You might be like, oh yeah, I'm getting the hang of this. 2x plus 1 is I'm doubling the input and then I'm adding 1. So I bet g inverse of x, I'd cut the input in half and then subtract 1. Right? Maybe it'd be 1/2 x minus 1. It turns out it's not. A little bit counterintuitive why it's not, but we could probably show that it's not by trying some examples. We could put numbers in and take numbers out and see what happens. Rather than show you what's not the answer, I'm going to show you what is the answer. If you're asked to find g inverse of x, there's this kind of, I guess it's a 4-step process. I don't know. You can number the steps however you want. But it'll work for any function. So it'll work for simple functions like this when you're finding your inverse, or more complicated functions, this or something even worse. As long as I give you a one-to-one function, you can always find the inverse using this method. The first step is, I guess you could consider it optional, but I prefer to change the g of x into a y. And the reason why is I'm going to do a whole bunch of algebra, and I don't want to have this weird symbol floating around in my equation. I don't want to subtract. I'm not comfortable subtracting g of x from both sides of the equation. You could do that, but it just looks really weird. I'd rather subtract y, for example, from both sides of the equation. So my first step is just changing the notation into this, just so it's easier to deal with. My second step is going back to the definition of an inverse function, or really maybe one of these 4 implications. And it's the one that talks about how when you're figuring out the inverse function, what the inverse function does is it switches the inputs and the outputs for the function. Well, the input for this function is x, and the output is y. So if I change the y into an x and the x into a y, What I now have is an equation that represents the inverse function. This is an equation that represents the function. This is an equation that represents the inverse function because I switch the inputs and the outputs, and that's exactly what an inverse function does. The problem with this equation is it's not in function notation. To get it into function notation, I have to have the output, the y, all by itself. So my first step, switch the g of x or f of x or whatever it is into a y. My second step, everywhere I see an x, write a y. Everywhere I see a y, write an x. And if you're keeping track and not memorizing, what you're doing is creating an equation here that represents the inverse function. And then your next step is to solve this equation for y. Solve this so that it looks like a function. Get the y all by itself. I don't know, maybe subtract 1 from both sides of the equation, and then divide both sides of the equation by 2. What you now have is this same equation. These two equations are equivalent, but this equation fits better into my functional notation. I can rewrite this, my final step. Instead of y, I could write g inverse of x, because the output to my inverse function I write as g inverse of x, and it's equal to x minus 1 over 2. Note that this is not the same as x divided by 2 minus 1. So it's not quite what you might have thought it is. This is the inverse function here. If you're not sure that you did it right, there's a lot of different ways you can check it. You could find the inverse of this function. You can go through these steps again and see that you get back here. The inverse of the inverse is the function. If you switch the input and the output for something that you already switched the input and the output for, you've gotten yourself right back to where you started. Another way you could check is you could compose these two functions together. You could find g of g inverse of x, or g inverse of g of x, whichever you prefer. So g of g inverse of x is g of x minus 1 over 2, right? Because g inverse of x I just figured out was x minus 1 over 2. A little line in here. G of x minus 1 over 2, no problem. Here's g of x. Here's the blueprint for g of x. Say when you put x in, this comes out. So what if instead of putting x in, you put this mess in? No problem. I would get 2 times, and then instead of writing this, I would write x minus 1 over 2 plus 1. And so, wait, what did you get here? What is this? Well, simplify this thing. This 2 and this 2 cancel out, so I get x minus 1 plus 1, which just equals x. What I just figured out is that when I compose g inverse and g of x, what comes out is just x. In other words, the input to this composite function is the exact same as the output of this composite function, which is the fourth of my implications of this definition. That's the recycling one, that when you put something into the function and then it rolls through the inverse function, you get right back where you started. Or in this case, I guess I did the inverse function first. So I took something over here, threw it into the inverse function, then let it run through the function, and what came out was exactly what I started with. That's what I just checked right here. You don't have to check this. I'm just showing how you can check these things. What do I want to do here? How are we doing on time? 18 minutes in. Okay, I'm going to show you 2 more things. I'm going to show you how to find the graph of an inverse function. If I graph a function, okay, first of all, let me graph f of x equals x squared. And you might be yelling at your computer right now, don't do that, that's bad. If you don't see why that's bad, that's okay. We'll see why it's bad in just a minute. Here's the graph of f of x equals x squared. There's lots of points on this graph, but I like to focus on 5 of them. These 5 right here. And what I'm going to try to do is draw the inverse of this function. And this is going to be bad. Why is this so bad? Why do I keep complaining about this? Well, this function's not 1-to-1. So I shouldn't be able to come up with the inverse of this function. But ignore that. Let's try it anyways. This point has an x-coordinate of 0 and a y-coordinate of 0. If I switch the x and the y, 0 and 0, I still get 0 and 0. So this point stays here. This point, x-coordinate of 1, y-coordinate of 1. Again, you switch the 1 and the 1, you still get 1 and 1, so nothing's really happening. What about this guy? This x-coordinate is 2, and this y-coordinate is 4. So if I wanted to find a point on the inverse function that corresponds with this, I wouldn't want 2, 4. I would instead want 4, 2. I'd want this point right here. So this point kind of goes here. This point has an x-coordinate of -1 and a y-coordinate of +1. So when I switch those around and get a point on the inverse function, the x-coordinate is +1 and the y-coordinate is -1. So this guy goes here. And similarly, this point that's at -2, 4 will move to 4, -2 when I'm trying to draw the inverse function. But look, if you tried to draw f inverse, maybe you connected the dots looking something like this, you'd get this graph, but the problem is this graph is not a function. Right? This graph does not pass the vertical line test. In fact, anytime my graph in blue doesn't pass the horizontal line test, my graph in red won't pass the vertical line test. That's exactly what I expected. Right? If my function is not one-to-one, it's not going to pass the horizontal line test. And therefore, its inverse won't pass the vertical line test, so I can't find the inverse of a function that's not one-to-one. Not a function. What I could do, and what I will end up doing, is I'll change this function. I will restrict the domain of this function. Essentially, I'll erase all this stuff up to 0. I'll say, okay, f of x equals x squared, but you are only allowed to put non-negative numbers into this machine. I'll make that criteria. I'll make it illegal to put -1 in the machine. The machine only accepts numbers from 0 up to infinity. By doing that, I essentially erase this half of the parabola, and what that does is it makes this function one-to-one. And now that this function is one-to-one, I can find its inverse function. In fact, it'll be the top half right here. So there is hope when a function is not one-to-one, and we'll see more examples of this as this goes on. But the point that I want to make is when you're first learning these, the function has to be one-to-one if you're going to find its inverse. What if it's not one-to-one? Well, then you're out of luck unless you want to change the function. The way you change the function is you restrict the domain, and it'll take some learning how exactly to restrict the domain. But you'll be able to restrict the domain to make a function that used to not be one-to-one, one-to-one. And in terms of the picture, I'm erasing the left half of this parabola. That makes this function one-to-one. Now all of a sudden I can find its inverse. Okay, here's a not one-to-one function. Let me graph for you a function that is one-to-one. And I'll just kind of draw this curve. I'll just be careful that I make it one-to-one. I got to be careful to make sure that I pass the horizontal line test. What if I asked you to draw the inverse of this function? Well, there's a couple different ways you could do it. You could try to find points on this graph like I did over there, and switch the inputs and the outputs and see where they go. You could try that. This one has an x-coordinate of -4 and a y-coordinate of -3. So on the inverse graph, I should use an x-coordinate of -3 and a y-coordinate of -4. This point's going to end up here. This point has an x-coordinate of -3 and a y-coordinate of just more than -1. So -3 and just more than -1, he'd go somewhere in there. And this guy right here looks to have an x-coordinate of -2 or so and a y-coordinate of 0. So I'll switch that to get a x-coordinate of 0 and a y-coordinate of roughly -2 and do that. And you do that same thing for the rest of these points. This guy is what, 2.5, 3, so I'll go to 3, 2.5, maybe something like this. And this guy is 4, 5, so I'll go to 5, 4, something like this. You might not like that. You might not like the idea of trying to ballpark points. Like, now how do you connect the dots? I mean, you can kind of just guess how to connect the dots, but how do you know how to connect the dots? Well, I can show you geometrically what's going on here. Another way to think about switching the inputs and the outputs of a graph is you're reflecting over the line y equals x. You're changing all the x's to y's and the y's to x's. Geometrically, that's the same as reflecting over this diagonal line right here. So really all I'm doing is drawing something in blue, trying as best I can, that matches, gives me a mirror image of the stuff that's in red on the other side there. Not perfect, but pretty close. Note you could have tried that same thing over here if you draw on this line y equals x. The reflection over this line of the blue is the red. So you can think about it as switching inputs and outputs, but just so you know, geometrically that's equivalent to thinking about it as reflecting over the line y equals x. Okay, the last thing that I want to do before I end this video is I want to do another one of these examples, just a harder one. Because what you'll see is the main thing you're trying to do when you're finding the inverse of a function, there's one step. I mean, the steps you do are always the same, but one of them can be a lot harder depending on the function you're given. So let's say I have a function, I don't know, h of x. And maybe I make that equal to x minus 1 divided by x plus 3. And I ask you to find h inverse of x. This is the question I'm asking you to do. First of all, you might be like, wait a minute, how do I even know this is one-to-one? It's a damn good question. I guess the only way you would know, well, this is one-to-one, trust me. How do you know it's one-to-one? Throw it in your graphing calculator and see that it passes the horizontal line test. That's one way you could do it. Base it just on the question that's being asked. You're being asked to find the inverse function. You can only find the inverse function if the function's one-to-one, so it must be one-to-one. But how do you do it? Well, just like I did up here, my first step, I don't like doing algebra with an h of x floating around. So instead of h of x, I'm going to write y. Y equals x minus 1 over x plus 3. My next step over here was to solve for y. No, that's not true. My next step over here was to switch the x's and the y's. Right? This is an equation that represents the function. I want an equation that represents the inverse function. So everywhere I see an x, I'm going to change it into a y. And everywhere I see a y, I'm going to change it into an x. That'll get me here. That's caught me up to this line right here. This next step is the one that can be really hard depending on the function you're given. Over here, my next step was to solve for y, and frankly, it wasn't that hard. I subtracted 1 and divided by 2. Over here, solving for y will be very challenging. And the reason it's challenging is because I have multiple y's, and I can't solve for y in terms of y. I have to make this so it's y equals something, and that something can't have any y's in it. That's hard to do algebraically. The trick for doing it when you have functions that look like this is you're going to end up getting all the terms that have a y in them on one side of the equation and factoring. But wait, we're several steps away from doing any of that stuff. This problem's hard because it's a fraction. Okay, so make it so it's not a fraction. Multiply both sides of the equation by y plus 3. I got x times y plus 3 equals y minus 1. Okay, I guess I see that this is equivalent to this. And I guess I didn't understand why you do it because you say you don't like fractions. But then where do you go from here? Well, my goal is to get all the y's together on one side of an equation. And that's hard to do with these parentheses here. Parentheses kind of inhibit me from moving pieces around as much as I'd like to. So I'm going to first get rid of these parentheses by distributing that x through. That gives me xy plus 3x equals y minus 1. And now I have this term has a y in it and this term has a y in it. So I'm going to collect all the terms that have y's in them on one side of the equation. Which side of the equation makes no difference, whatever you want. I'm going to collect all my y's on the right side of the equation. You could have chosen to do that differently. I'm going to subtract xy from both sides and add 1 to both sides to get me here. The nice thing about this here is if you factor a y out from the right-hand side, what you've now done is rewritten this thing so that you only use the letter y one time. So I guess I did 2 steps there. I switched this side these were on. I kind of wanted my y's to be on the left, so I just wrote this thing over on the left. And then I said, wait, as long as I'm writing it, why don't I factor out a y from each of these 2 terms so I get y times 1 minus x. The reason I did that is down here, the problem with this is there's 2 y's. The solution is to factor, now you only have 1 y. And you have 1 y, solve for it, no problem. Get it by itself. Divide by 1 minus x. You get 3x plus 1 divided by 1 minus x. Just an FYI, this is the same as negative 3x minus 1 divided by x minus 1. It's also equal to a lot of different things. The reason I chose this form is in your process of solving, had you done things slightly differently, you might have come up with this answer, and I don't want you to think you were getting the wrong answer. Often I'm cool with students leaving their answer right here, but technically I was asked to find h inverse of x. I wasn't asked to find y anything. So really I should say h inverse of x is equal to 3x plus 1 over 1 minus x and call that my solution. I think I'm going to end this summary here. I think that's a pretty good summary of what you do in this section. The one thing that I haven't talked about is what you do in the case when you're given a function that's not one-to-one and how you restrict the domain and find its inverse. I alluded to that a little bit in this picture down here, but I think that's kind of an expert level thing. So I'll go through and I'll work the examples in this section and see how much your book gets into it, and then I'll either list that in one of those examples or I'll list it in the bonus material for this section. So I'm going to end this summary here.